Welcome, dear students, to this new video on process concept. At the end of the previous video, I told you that we will be discussing about operations on processes in the next video. But before that, today we will be discussing about process schedulers, where we will be covering about short-term schedulers, then long-term schedulers, medium-term schedulers, and at last context switching. So let's begin with the schedulers now. So far we have read that during its lifetime, a process migrates between ready queue and various waiting queues. And it is the scheduler that picks a process from the processes that are present in the ready queue, and the process which is chosen is forwarded to the CPU for its execution. In case of batch systems, the number of processes which are submitted to the system are more than that those can be executed immediately. So these processes cannot be transferred to the ready queue. In fact, these additional processes are stored on the disk from where they are transferred later on to memory for execution. So what I'm trying to say over here is actually the number of processes which needs to be submitted to the ready queue are quite high in number, and we cannot forward all those processes onto the ready queue. As far as ready queue is concerned, it maintains all the processes in the main memory, and the main memory cannot accommodate all those processes. So what happens over here is those processes are stored onto the disk, and out of those processes which are stored on the disk, few of them are brought into the main memory. Fine. And where we are referring to that, it is a ready queue of processes. So all these processes which are there in the ready queue, in fact they are on the main memory. So these processes, out of these processes, depending upon the number of CPU cores, some processes are chosen and they are transferred onto each of the cores of the CPU where they will be executing. Fine. So before this, if you see, I have told you some processes are residing on the disk because the number of processes were large, so all of them were not residing in the ready queue. So out of these, few of them are transferred from disk onto ready queue for execution. So who does this job of transferring the processes from disk onto this ready queue? So it is the long-term scheduler which picks the processes from the disk and transfers it to the main memory. Then those processes are residing in the ready queue, but as of now they are not executing. In fact, the processes from the ready queue are supposed to be transferred to the CPU. Depending upon the number of cores available with the CPU, that many number of processes can be transferred to each of these cores. So what happens over here is, suppose a ready queue is having as of now 6 processes. Fine. And all the cores of the CPU are idle, and there are suppose 3 CPU cores. So out of these 6 processes, only three processes can be transferred to the CPU, to each one process to each CPU core. So it is the short-term scheduler. It is the short-term scheduler which picks the processes amongst all the processes which are residing in the main memory or in the ready queue presently. So out of that, few processes are fetched and are allocated to CPU for execution. The short-term scheduler selects a process from the main memory whenever the CPU is free. So what happens over here is what I'm trying to say. Suppose as of now, the short-term scheduler has selected process 1, 2 and 3 for execution. So let's say these three processes are assigned to the three cores. Core 1, suppose core 2 and core 3. Let's name them as this. Core 1, core 2 and core 3. And process 1 is assigned to core 1, process 2 is assigned to core 2 and process 3 is assigned to core 3. So these processes will be executing over here with the cores. Let's suppose that at some point in time this process PE3 has completed its execution. So once it has completed its execution, this CPU core is now free. So in that case, the short-term scheduler, that is this one, will fetch the another process from the list of available processes in the ready queue and will allocate that process to the ideal core of the CPU. So let's suppose it fetches process P4 now, and that P4 is assigned to the idle core of the CPU, and this P4 is now executing. Further, different processes may need different amount of CPU time to complete its execution. What I mean to say over here is each process needs to spend different amount of time for its execution. Let's suppose P1 needs 10 milliseconds, P2 needs, let's suppose, 25 milliseconds, and P3 needs 3 milliseconds to spend with the CPU to complete its execution. So it is not like that each once the process is assigned to the CPU, so it will only leave the control of the CPU upon completion of its execution. It is not like that. So the OS maintains a kind of scheduling where each of the processes, those who are executing or those who are waiting, it maintains the execution in such a way that each of these processes are getting the allocation of CPU within a certain span of time. So if you see over here, we have to note one thing over here. If the process is a CPU bound process, actually the process can be a CPU bound process or it can be an IO bound process. So we can categorize the processes as CPU bound or we can categorize it as IO bound. Fine, we can categorize the processes into two ways. If the process is CPU bound process, it will need CPU for larger amount of time in comparison to a process which is an IO bound process which may execute only for few milliseconds before the process waits for an IO request. What I mean to say over here is if we go more into the details of this thing, the processes can be categorized as IO bound processes and CPU bound processes. So if you see over here, the IO bound processes are those which spend more of their time doing some IO activity rather than the computations. That means their CPU bursts are small, means they need CPU for only a small period of time. Similarly, if we talk of CPU bound processes, basically these processes spend more time doing computations rather than spending time with IO. So they have long CPU bursts. So a process executes for some milliseconds, and again a short-term scheduler fetches a process from the main memory and passes it to CPU for execution. Thus, a short-term scheduler executes quite frequently. So what I mean to say over here is, suppose a process was executing in one of the cores over here, and what happened over here is this process P1 was executing, and let's assume that it was an IO bound process. That means it was supposed to spend a small amount of time with CPU because it was IO bound process. So during its execution, it was now required to perform some IO activity. So this process is shifted to the waiting queue of IO. From the basically it is shifted from the CPU core to the waiting queue of IO. That means what happens over here is once it is shifted, this CPU core is now free because process P1 is shifted now. So the short-term scheduler basically will select the next process which is available in the ready queue for its turn of execution and will assign this CPU core to that new process. That is why I'm saying a process may execute for some milliseconds, and again the short-term scheduler fetches a process from the main memory and passes it to CPU for execution. So this short-term scheduler actually is executing quite frequently because the processes which are there with these cores, there may be a case that some of them might be executing with CPU for a longer period of time. Otherwise, there might be some processes which will be executing for shorter period of time. So we want our system or our CPU to be busy for most of the times. So in that case, the moment the CPU core is free, the short-term scheduler will fetch a process from the ready queue and will hand it over onto the CPU core, so that CPU core is working on that new process now. What I've told you over here is the short-term scheduler executes quite frequently. It needs to be very fast. It must operate very fast. In comparison to it, the long-term scheduler executes quite infrequently, maybe after some seconds or minutes, whereas in case of the short-term scheduler, it may have to execute after every few milliseconds. So in long-term scheduler, it executes infrequently, as I've told you, maybe in some seconds or in few minutes when the new process are created in the system. So as I've told you in the beginning, the moment the new processes are created in the system, they are not brought into the main memory on the or in the ready queue immediately. Let's suppose already the ready queue is having a long list of processes, and memory is unable to accommodate new processes within itself because the memory is already occupied. So in the meantime, what will happen of about these new processes which are created? So these new processes are not brought directly into the main memory, but they are stored on the disk. Fine. And as I've told you, the long-term scheduler actually, whenever the new process is created, it is basically allocated space in the disk. So it resides in the disk, and when it is observed that the memory is free, so in that scenario, new processes are shifted from the disk onto the memory or onto the ready queue. So who does this job? It is the long-term scheduler. So long-term scheduler basically also controls the degree of multi-programming. That is, how many processes are migrated to the main memory from the disk. So if we want to increase the degree of multi-programming, we will be doing it only if it is observed that there is ample memory which is freely available to accommodate the new processes. So actually this long-term scheduler also helps in controlling the degree of multi-programming. What if suppose a question arises that already the number of processes are too much in the main memory, and the system is working quite slowly in that scenario. So even we can bring back or we can deallocate some of the processes from the main memory, and we can bring them back later on for execution. So the degree of multi-programming is stable if the average rate of process completion is same as that of process creation. So suppose we want to have a stable degree of multi-programming. So what happens over there is LTS will only execute. That means it will bring the process from the disk onto the main memory only if some of the processes which were already there in the main memory have completed their execution. For example, suppose as of now, earlier there were 6 processes in the main memory and they were executing with the CPU. Out of those 6 processes, So we can assume that the degree of multi-programming is 6. Fine. So what happens over here is, suppose process 4 and 5 have completed. So as of now, only 4 processes are competing for the CPU, and they are getting these 3 cores. So in that case, the long-term scheduler can bring 2 more processes from this disk onto the main memory, so that again there are 6 processes in the ready queue, out of which some of them are executing with the CPU and some of them are waiting. So depending upon how many processes are completing their job and they are terminating, accordingly the number of processes are brought from the disk onto the main memory. So the degree of multiprogramming is stable if average rate of process completion is same as that of process creation. So I hope you got the point, where we can say that long-term scheduler is invoked only when a process has completed its execution and is terminating. Now, as I have already given you a brief description or introduction about CPU bound and IO bound processes, uh, so it is quite important for the long-term scheduler to select a mixed set of IO and CPU bound processes to be forwarded to the main memory, because if all the processes are IO bound, there will be a large IO waiting queue, whereas ready queue will be empty. CPU in that case will stay idle, and short-term scheduler will also be doing nothing. On the other hand, if mainly the processes are CPU bound, then IO waiting queues will be empty for most of the times and the devices will remain unused. So to have an optimal performance from the system, we need to have a good process mix inside the ready queue or inside the main memory. So what I'm trying to say over here is, as I've told you earlier, that it is the LTS basically who shifts the processes from main memory onto the ready queue. This job is done by the long-term scheduler. Let's assume a case that LTS has chosen process P1, P2 and P3, and it shifts these processes onto the main memory. Fine. Onto the ready queue. Sorry, this was not main memory. In fact, it was disk. So I repeat my lines. I am saying that long-term scheduler is, upon creation of a process, long-term scheduler basically either stores them onto the disk, and later on when there is a need, it shifts these processes from disk onto the ready queue, or to the main memory. Now let's suppose presently and this long-term scheduler has shifted process P1, P2 and P3 onto the ready queue. Fine. And uh, let's assume that all these 3 processes are CPU bound processes. This means what? If P1, P2, P3, all of them are CPU bound processes, that means they will be spending maximum of their time with the CPU. So if all the processes are spending more time with the CPU, in that case the waiting queue of devices, IO devices, it will be empty, because very few processes will come in the waiting queue and will ask for IO devices for their execution related task. So in that case, we are underutilizing this queue. On the other hand, let's assume the opposite to this. Let's suppose that P1, P2, P3 are, all of them are IO bound processes. So in that case, what will happen? These processes will spend a small amount of time with the CPU. Fine. And one, after spending that short span of time with CPU, they will switch on to the waiting queue of what? Of IO devices, and they will demand for some input or output devices. And if the number of all those processes which is demanding some IO related activity, they all will be in the waiting queue. So in that scenario, the CPU will stay idle, because whatever job these P1, P2 and P3 were supposed to do with the CPU, they have done. And there is no other process in the ready queue which needs CPU now. In fact, CPU was executing three jobs and they have not completed yet, but they have done a part of their job with CPU, but are now waiting but are now waiting for some IO activity. And because there are many processes which are waiting for some IO activity, and each of these processes, let's suppose, is demanding disk, or maybe is demanding magnetic tape to complete their IO activity. And the number of tapes, let's suppose, are not are not in multiple instances. We are having only one copy of tape, so there will be a queue of processes which will be waiting for the tape. So in that case, before they can do their activity with tape, they cannot move on to the ready queue and later on to the CPU. So ready queue for majority of time will be short of the processes. In this case, automatically, if ready queue is not having processes, so CPU will also stay idle. So in that case, if you see, with regard to these two things, it is always better to have a process mix in terms of the processes which are transferred onto the ready queue. It is, that is, we can have even number of processes for CPU also, CPU bound processes also, as well as IO bound processes also. In that scenario, our system will give us a good performance. Now, apart from these two schedulers, that is short-term scheduler and long-term scheduler, there is another category of scheduler which is also known as medium-term scheduler. It is also called swapping. So sometimes there is a scenario that when a memory is overly occupied and the system performance is degrading, because each of the processes needs a certain amount of memory to do its job. So if the number of processes available in the memory are quite large, in that case, the processes won't be able to execute in a faster way. In fact, there will be an issue regarding getting some memory to complete their execution. So the system's performance will be degrading in that case. So in that case, we need to reduce the number of processes in the main memory. That is, we need to reduce the degree of multi-programming. So in this case, some processes which are in active contention of CPU are removed from the main memory and are saved onto the disk. So what I'm trying to say over here is, let's suppose that as of now, there were 10 processes, I would say, in the in the ready queue. Because the number of processes were large, I'm just assuming one number, it can be more than that also. And obviously these are the active processes which are there in the main memory, which are consuming some main memory. But because the number of processes are large, in that case, maybe there is an issue with regard to assigning memory to all of these processes during its execution. So obviously, if the processes are not getting ample amount of memory to complete their execution, in that case the system's performance will be degrading. So if we see over here, earlier, because the number of processes were large, so the degree of multi-programming was also on the higher side. But though the degree of multi-programming is on the higher side, but the performance of the system was degrading. Now we need to improve this performance. So for that, what we can do is, we can actually choose some processes which were there for the active contention of CPU. We can remove those processes from this ready queue or from the main memory and stored them onto the disk. So what I mean to say over here is, let's suppose we choose 3 processes out of these 10 which were in active contention of CPU, and we are storing them to the disk. So let's suppose I've chosen P2, I means the OS has chosen P2, P3 and P4. So this means that out of 10, 3 have been removed from the ready queue or from the main memory. So only 7 processes are over there uh, which are now in active contention of CPU, and 3 are removed. Now we are storing these 3 processes on the disk. Now question rises, why we need to store them onto the disk? Because we are storing them to the disk because P2, P3 and P4, let's suppose they were these 3 processes who were removed from the ready queue. They have executed partially. That is, they have not yet completed their job, but their execution has been done partially. So we are saving their state onto the disk. State means the point till they have executed whatever values they were having at that time, or whatever the situation was over there with regard to these processes at that time, that state is saved onto the disk. So the idea behind this is that later on, when these processes will be transferred from disk onto ready queue, they can begin their execution exactly from the place from where it left. So this is only feasible if their previous state was saved. So when a process, what I'm saying is, so when a process again comes for execution, it can continue from the point from which it left earlier. So if you see, even if you observe over here in this diagram, so the as far as this arrow is concerned, it represents the processes which are coming from the disk, that is, which the long-term scheduler is basically dealing with. Long-term scheduler is basically providing the processes from the disk, and these processes are now transferred onto the ready queue. So as I've told you, we were having 10 processes from P1 to P10 if they are numbered. So they are sent on to CPU depending upon the number of cores. So these processes are executing over here. If some process completes its job, it will come to an end. That means it is terminated. But in case a process needs to perform some IO activity, in that case, that process is shifted onto the IO waiting queue, where they will perform their activity with regard to that IO, and then will be switched from this IO onto the ready queue again. And now here again the process is waiting for the CPU to complete its remaining execution. But what happened over here, let's suppose in this scenario, because the number of processes which were actively involved in CPU's contention, they were quite high in number, because of which the system's performance was degrading. So once they were executing, now they are not brought into the ready queue, because we want to reduce the degree of multiprogramming so that we can save system from degradation. So in that case, the process is now swapped out from the active contention of memory, and they are placed the partially executed processes. Because why I'm saying partially, because some part of the process is executed, so this partially executed process is swapped out and is stored on the disk. Later on, when it is observed that the degree of multiprogramming has reduced, or ample amount of memory is free, these processes which were partially executed are now swapped in from the disk and are placed on the ready queue, and now they can complete their pending execution. So I hope you got the idea. What I'm trying to say over here is, the medium term scheduler basically is controlling the degree of multiprogramming. It swaps in or swaps out the processes depending upon the availability of space in the main memory. Now if you now let's move on to the next topic, that is context switching. So if you observe over here, The question arises, what actually is a context switch? So when a CPU switches to another process, so what I mean to say over here is, as of now process P1 was executing. So fine, we let's suppose we are assuming that we are having a CPU where there is only a single core. Fine, single core of the CPU. Now this process was executing with the CPU. Okay, so before it could complete its execution, let's suppose this process was interrupted, and the interrupt was done by a higher priority process. A new process came, let's suppose P2 came, and this P2 process was having higher priority as compared to P1. Fine, in that case this P1 has to leave the control of CPU in between. I mean to say, this process has not yet completed its execution, but because a higher priority process has came, so we need to free the CPU from process P1 and allocate the CPU to process P2. But P1 has executed partially. So what is done over here is, whatever the state was of process P1 when this interrupt was over there, that state of this process P1 is saved. So if you remember, earlier we have read about a term that is called process control block. This is a unique block with regard to every process, which basically contains the complete information about the current state of the process. So that current state of the process which is there in the PCB for process P1 is saved, and then the process control block of process P2 is loaded onto the memory so that CPU can start working on process P2. Question is, why we are saving the state of process P1? The state of process P1 is saved so that later on, when this process again comes for execution, we can begin from the place from where it left, because this process was partially executed, so it should continue for the remaining part of job only, rather than going for re-execution of the entire process. It is only feasible if the state at which this process was asked to leave the control of CPU, that state is saved. Similarly, process P2, before it can begin its execution, first of all we need to load the state of this process onto memory. Then only CPU will be able to work with the process P2. So if we talk of context switch means saving the state of currently executing process and loading the state of new process. That is basically called a context switch. And context of a process is represented in the PCB. This PCB contains a huge amount of information, out of which one of them is the process state. Second thing is the memory management information, and likewise it may contain information like what all resources are allocated to the process, or what all IO activities or what all IO events are supposed to be done. So all this set of information is available in the PCB of that process. Actually, there's one more thing, that is context switch time is an overhead, because system is not doing any useful work while switching is being done. The useful work is done only when the CPU is working with the process, or the process is doing some IO related activity. But in this scenario, neither the process is doing some IO activity nor the process is executing with the CPU. The only thing which is done during this context switch time is we are saving the state of currently executing process, plus we are, after that we are loading the state of the new process. So neither CPU is being used nor the IO activity is being done. So actually uh, no productive job is being done during this phase. So that is why actually this context switch time is treated as an overhead only. So if you observe, we have covered in one of the figures. I'm going to show that figure again over here. If you remember over here, if we talk of the productive work was only, if you observe, when the processes were executing. The process P0 was executing for this much amount of time, then process P1 was executing for this much amount of time, and then again P0 was executing for this much amount of time. Here what we are saying, actually P1 was executing, then P2 came for execution, then again P1 got the access of execution. So the sequence of execution was this, beginning with P1, then P2, and then P1. So if you see, process P0 was executing. Altogether an interrupt occurred, and the demand was that to hand over the control of the CPU to process P1 now. So before that, I have told you we need to save the state of currently active process, and that currently active process is which? It is P0. So we are saving the state of process P0. So this state is saved for process P0. Also, we are reloading the state of process P1. Now, once the state of process P1 is loaded, process P1 is executing. Then again, suppose the control was transferred to process P1. That means we have to save the state of this process first. So we have saved the state of this process first. Then because P1 was to execute, we need to reload the state of, so that now CPU can work on with P0. So if you see, during this phase, fine, as well as during this phase, actually the context switch was going on, and during this phase CPU was idle. That is why we are saying that actually context switch is an overhead. So with this we come to the end of this video, and I hope that uh, you have got a fair idea of process schedulers. In the next video we will discuss about operations of on processes. Thank you.